So hello everyone. My name is Shivcharan Puri, Assistant Professor, EC Department, Asansol College. So this is the third video. So in the previous tutorial video, we have talked about the realization of Boolean functions using the sum of product expression and the product of sum expressions, which is represented by mean term for SOP and max term for cost. We have also seen that any combinational circuit. So we have also seen that for n input variable, we will be having 2 to the power of n mean terms. Okay. So if we want to realize a logical circuit, then we will be having a truth table, the Boolean function for the function or the output rather, and eventually the whole logical circuit. In the process, we have taken the help of the basic identities of Boolean algebra to solve, or rather to simplify, the hectic Boolean expressions. To simplify the circuit, to make the circuit optimal. Okay. So as you can see here, many different logical diagrams are possible for the given function. You can see here f is equal to abc plus abc bar plus a bar c. So this is a circuit. So if we can simplify it, c plus c bar is 1. So it will be ab plus a bar c, this one, or this one. Okay. So one function can have different solution of the logical circuit, but the optimal one is that which uses the least resources in all. Okay. So let us go for the simplification part. So if we want to simplify it further without using the De Morgan's theorem or Boolean algebra, the best, or rather the simplistic way to solve expression is by introducing K-map into account. So K-map is a simple procedure for simplifying Boolean expression. Okay. So what happens in a K-map? You can see here, it is having n cells. It is having K-map for an n input digital logic code, n variable. So if there is n variable, you will be having total of 2 to the power of n cell in a K-map. So K-map, you can see here. So if you are having 2 variable, okay, suppose if you are having 2 variable, then the number of cells will be 4. Okay, number of cells will be 4. Okay, so suppose if you are having 4 variable, so the number of cell will be now increased to 4 into 4, that is 16 cells. Okay, so we put the valid outputs for the corresponding min terms as 1. You can see here. So this, if this is xy, so if this is 1 0, for 1 0 combination, my output is high or valid, it has to be 1. For 1 1 combination, my output is valid, then it is, so wherever there is a valid expression, okay, for a function, as you can see here, 0 1 is 1, 1 0 is 1, 1 1 is 1. Okay, so this will also be 1. Okay, as you can see here, 1 2 3, so these all are 1. Okay, so for 1 you can see here this one, and for 1 2 this you can see 0 1 is 1 and 1 1 is, you can see here 0 1 is this one. Okay, so now let us go with this table. So suppose we are having this one, okay, and these are the valid or the invalid outputs. Okay, so as you can see here, my output is valid for summation of min term of the summation of min term of 1 2 4 1 to 4. Okay, so only for summation of small m min term of 1 to 4 I have valid outputs. So what we will do, and this is basically 3 variable. 3 variable means 8 cell. Okay, so what we will do, we will take here 2 cells in the row, which is x is equal to, which corresponds to x is equal to 0 and x is equal to 1, that is x bar and x. And columns will be 4 0 0 0 1 1 0 1 1. Remember here, it is 0 0 0 1, then 1 1, then 1 0. Okay, it is not following binary as 0 0 0 1 1 0 1 1. Why? Because it is based on, this whole Cray map is based on Cray code. Okay, and it clearly follows the pattern of the Cray code. Okay, so there will be 1 1 over here. So we have valid output for 1, as you can see here, 0 0 1. So 1, this is the 1 cell. So we are having here 1 here, or the valid here, you can, it is surrounded in as a square. Then we have 2, so 0 1 0, you see here this one. Okay, then we have for this fourth cell is now valid. Okay, rest all are zeros for min term. Okay, so as you can see here, it is 0 1 0 1 1. So here is 1, here is 1, here is 1. So in this way we used to put the put the ones in the cell of the K-map. So similarly, for a different function, which is here, which consists of 4 variables. So 4 variables means 2 to the power of 4, that is 16 cells. So we will be having 16 cells. Okay, row into column. You can see here 0 0 0 0 0 0 0 0 1 is 1, 0 0 1 1 is 3, 0 0 1 0 is 2. So similarly, these are all the places. Okay, and this output is basically valid for 1 3 6 8 9 11 14. Clearly you can see here 1 3. So number of so the ones has to be put down in the corresponding valid cell. Okay, in the corresponding valid cell. Okay, and then we have to simplify. Okay, so if we will be having, what is the process of simplification I want to explain. We want you see here, suppose we are having this f is equal to xy bar plus xy. So it is simply the number of 1 will be 1 0 and 1 1. That is summation of m of 2 and 3. Okay, and 2 variable. So there in 2 variable there will be 4 cell 0 1 2 3. In this 4 cell, the valid cells are, or the cell which has the 1 is 2 and 3. So we put here 1 0 1 1. So here will be 1, here will be 1. Okay. So how do we merge, or rather pair a cell to simplify a logical expression? This is the first step for two variables. So as you can see here, we will pair this. We will say it to be a dual. Okay. Okay. And what happens is we will make a dual, and we will reach a conclusion by looking into the rows and columns. So as you can see here, this, you can say it like this dual is because of this row and these two columns. Okay. So what is in this row? Simply X, isn't it? No. And what is in these columns? It is 0 and 1. That means Y is equal to 0, Y is equal to 1. What kind of arrangement is this? Sum of products. These are all min terms. That means this columns is basically this columns. If we are clubbing these two, rather we are making a dual pair over here, then this will be y bar plus y. So this is actually 1. So the only left out, as I told you, row into column. In column we have nothing, because 0 and 1 opposite means y bar plus y. Y plus y bar is equal to 1 into row, and in the row there is 1. That means this correspond to x, is this correspond to x. So we'll be having x into 1 is equal to x. You see here the simplified form is now achieved using the Karnaugh map, which is the beauty and of the Karnaugh map, that it will give you the simplest logical expression for any arrangement. Okay. So now let us talk of this. Okay. So now let us talk of this one. U bar, V bar, W bar, X bar, plus U bar, V bar, W bar, X, plus U bar, V bar, W, X, plus U bar, V bar, W, X bar, which correspond to min term of 0, 0, 0, 0. That means summation of m of 0, comma, 0, 0, 0, 1. That means 1. That means 0, comma 1. 0, 0, 1, 1. It's nothing but 3. So that means 0, 1, 3, and 0, 0, 1, 0. This is actually 2. So 0, 1, 2, 3. Okay. So as you can see here, if you plot it, if you just put this summation of m of 0, 1, 2, 3, okay, and if you are having 4 variables, you'll be having 16 combinations. You'll be eventually reaching this conclusion. Now, what are the types of pairing you can make? See, our always objective is to pair uniquely. Okay, it's very important. I'm repeating it again. We should be able to pair uniquely, the optimal, the most optimized one. Okay. Now, what are the kind of pairs? You can have a dual, as I showed you here. This is a dual. Okay. Now, you can also have a quad like this. This is a quad. Okay. This is also a horizontal quad. Okay. You can have a octal like this. So these are all the different form of pairing. So dual, quad, octal. Okay. So the most number of pairing you can do, the most simplified the expressions will be eventually. So, which is actually our prime target. Okay. To pair the most. But what I want to what I was willing to share with you is that, suppose I have paired this one. So you can see here, no overlapping between these two. Okay, we will overlap. Actually, we will overlap, but only in the condition when it is unpaired. When it is helpless, in that condition, you should pair. Otherwise, you should make the pairing unique. So suppose this is a quad here. This is another quad here. This is another quad here. No one is left out. So definitely there is no need of pairing it again. Okay. So likewise, we can also pair between this one and this one. The end, all the ends, edges here, end this one, and this whole end can actually merge. So there is no problem. Similarly, between this horizontal, this whole can merge, but between this you cannot merge. Okay, between this you cannot make a pair. Okay, you cannot make a pair. Also, between the diagonals, you cannot make a pair. Okay, so the limitation is that you should only pair the adjacent. Okay, and these two verticals can make a pair, and these two horizontals can make a pair. In between, it can't make a pair. Only it can make a pair if it is having the adjacent one, but can't pair diagonally. It will violate. Okay, so these are the rules of the pairing. So one pair is basically a dual. So if it is two pairs, it is basically a quad, and if there is a four pairs, it is basically oct, as in this particular case. Okay, as you can see here, it will give you the most simplified form. So once we get the simplified form, the only thing which is to be left out is actually this expressing it with the basic gates or the logical circuitry. Okay. And this logical circuitry will be the most optimal, which we have got by successive reductions or optimization using K-map, which is a brilliant technique to simplify any hectic or clumsy logical expressions otherwise. So you can see here. So if we want to simplify using POS, okay. So if we want to simplify it using POS, we have to go with the same method. We have to go with the same method. Okay. Just what we have to do is we have to just tune the rules of the game, whereby we will consider the whole arrangement to be actually a POS, and therefore we are pairing 0 over here and not so. Other everything remains same. Okay. So if suppose, so if this is actually a pair, and this correspond to for this row correspond for X and this column corresponds for Y. Let us take an example. So if this two is the pair 0 0 0 1. So between these two between these these two cells in these two columns, only left out will be 0 0 0 1. Only left out will be Y bar. Okay. Only left out will be Y bar, and this actually corresponds for X 0 1. You can see here this corresponds to X, isn't it? So this corresponds to X. You can see here X is equal to 0, X is equal to 1. Okay. So but one thing you should remember, because we generally used to jump for conclusions. In POS expression, just want to remind you, in POS expression, 1 was actually the inverted value. So this is actually now for 1, not X, it's actually X bar. Okay. And similarly, 0 0 0 1, 1 0 will go on. So basically 0 means actually now it is Y. Okay. It's actually Y. Okay. So for POS expression, it will be X. plus y, not sub where this will be multiplied. Now this is a pos where it is product of sum. Okay, so now this will be x plus y for this one into the, whatever this one, and for all the pairing you will be having solutions for pos forms that you have to take care of. Another thing which comes while minimizing K-map is the don't care expressions. So don't care expressions we will talk in the combinational circuit succeeding videos. So don't suppose we are having a digital phenomena like XS3 code. So let us take an example of XS3 code. So in XS3 code, the code always exits from binary by 3. So when binary is 0, 0, 0, 0, rather 0, XS3 is 3. Okay. So when it is 12, XS3 is 15. So when binary is 13, XS3 goes for don't care because it is invalid, or rather forbidden. So the rest of the binary states, that is 13, 14, 15, are actually considered to be the don't care conditions. Okay. Now, what we do with the don't care conditions? Okay. So suppose if we take, we will talk about the XS3 code. So suppose if it is the XS3 code along with all the valid expressions, we will also consider plus d of summation of d of, rather you can, we used to write summation of small m, capital M, or a small d, okay, d of 13, 14, 15. Okay, so 13, 14, 15 for XS3 is actually a don't care condition. Now what do we do with all these d's? Simply, we used to, if you really require, if you see that for simplifying, you require the d in the cell, like you can see here, if I take this 2d, what will happen is basically I can form a quad over here. Genuinely in this type of situation, we should take this, we should consider this. Okay, but you see here is one more d. Okay, one more door, here is one more d. So if I club this, I get nothing because it is don't care. So in this situation, we will not take it. So according to our convenience, we have to take care of the don't care conditions for pairing. Okay, while coming in the succeeding sections of the combinational logic circuits, we will see, or rather apply extensively, the basic rules of the K-map and the most simplified circuit we will get using K-map. Thank you.